In the previous sections, we saw that object detection algorithms are made of two main parts. That is a feature extraction and machine learning, where these vital features which have been extracted from the input images are used by these machine learning algorithms to locate correctly where we have an object in the image and also what kind of object we are having. The next set of algorithms which we shall look at function slightly differently, though the concepts of feature extraction and machine learning are still part of them. These algorithms are known as deep learning algorithms, and deep learning is a branch of machine learning which are made principally of neural networks. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. In essence, you could look at a neural network as a machine learning algorithm made of an input layer, several hidden layers. In this case, we're just dealing with one hidden layer. So we have this hidden layer right here. This is the hidden layer. This is the input layer, and then an output layer. Now you'll also notice that each of these layers have a given number of units right here, which we'll call neurons. And just like every machine learning algorithm, the way we are going to train this model or train this neural network is by inputting, say, hundreds of thousands of input-output pairs, and then this machine learning model is going to learn from this different input-output pairs such that when presented with new information, the neural network can make the right decision. To better understand this, let's take this simple example. Let's suppose we want to build a model which takes in an input, like say this red car, and correctly says that the inputted car is actually a red car. So we have this car, this input image. Actually, it's not like the physical car, but the car's image, which is passed into our neural network. If you notice, we have the three dots here to show that we could have so many inputs here, or so many input units. So we take this image. Recall that the image could be broken up into a three-dimensional math object, where this matrix we shall have here, the three different matrices, will contain the different value of the pixels for the different values for each and every pixel we have in the image. And so here we could have, as we have said already, hundreds of thousands of these kinds of images, but let's consider just a single pair. So here we have a red car, and then the output is obviously red. So here we would want to have this here. And then in the case where we have a blue car, we want to have the output to be blue. Nonetheless, note that if those inputs we have right here are these matrices, then the output would be some sort of matrix. So here we would have an output which will take two values. So we're not going to output the neural network doesn't understand these colors like this. They actually understand numbers. So we would have this red. We could say, for example, that each time our output, because here we have two possibilities. So let's do this. Let's just put it this way. So each time our output gives us a 0 on the first position and a 1 on the second position, then it's a blue. And each time our output gives us a 1 right here and then a 0 right here, then it's a red. So let's draw it this way. We have 1 0 for red and then 0 1 for blue. Now, just like with the inputs and the outputs where we're having these numbers, these hidden layers would get this kinds of numbers. So here we would have a value, would be some sort of array of some certain dimension. An array here basically is just like this matrix. And when we have a 2D array, we have a simple matrix like this one. When we have a 3D array, it simply means we've stacked several 2D matrices like this. So here we could have a certain dimensional array, and with this at this level, and this, and this, and this, and finally this. So at the end of the day, this neural network basically understands numbers. And then to get these values from the inputs, we have what we call weights right here. We have weights. We have actually weights and biases, but let's suppose we have just weights. So let's say we have weights. So each of these lines here connecting one neuron to another is actually a weight. So we have a weight here, and then what goes on is actually that we take this inputs and multiply by this weights, and add with a bias to obtain this output right here. As we said, we're not going to get into details in this course, but it's important for you to understand this concept. Now, the reason why we actually go through a training process is to tune these weights. So these weights right here are the parameters of our model. So we want to tune these weights. The weights are here, and we also have weights right here. Let's take this off. We also have weights right here. So each line we have in here, see, you have a weight, and they all have different values. So all these weights have different values. We could say W1, 2, 3, 4, 5 to N. Let's say 2 or 1N, and so on and so forth. We could have different indices for these different weights, and that's it. So as we're saying, each time you go through training, you actually modify the values of those weights. The reason why you want to modify the values of these weights is because you want to obtain values for these weights which permit us get reasonable outputs. That is, we want to get a certain group of values of weights such that whenever you come in with a blue car like this, all these computations will lead us to an output like this. And whenever you come up with a red car like this, all these computations will lead us to an output like this. And so we could look at these weights like some sort of knobs which you actually tune during the training process. So we initialize this weight. So initially you would just pass in this kind of car and you would have some crazy output here. It may give you this or it may give you this output. So the model at that moment isn't very intelligent. But as soon as you start training with hundreds of thousands of images, we actually get to modify or tune these values for the weights. So we have this knob which is been turned around. So we turn around or we modify these values of the weights as we pass in different images or different inputs into this neural network, and then we get to a point where the neural network modifies its parameters such that when shown a particular image, the neural network now is intelligent enough to provide us with reasonable outputs. That said, don't get scared with all this theory. We're going to be using or making use of such concepts to better understand the practice which we shall be working on shortly. Let's go a step further to better understand the training process. Now, supposing we have, as we have said already, hundreds of thousands, even millions of images which have to be passed into our neural network in order to train it, that is in order to tune all these different parameters, then you would have this image right here coming in with its own output. So recall we're having like the input and the correct output. So here we would have, let's take this off, here we would have this input with its own output. So we would have something like this, 0, 1. And then for this, for example, we'll have this with its own output. We'll be having 1, rather it's actually 0, 1 here because we suppose the blue is on the second position and then the red is on the first position. So let's take this off from here, and then we have here 1 so that the output is red, a red car, and we don't have a blue car. So that's it. Now we have this input output pairs, this input here with this input with its own output, and then from here we undergo a training process. Now the way we trick our neural network to modify these different parameters in a way that we are going to have a model which now takes any kind of input and knows what color it is that we are going to use a loss function. So this loss function can also be known as an error sanctioning function or a cost function, but we will retain the term error sanctioning function. Now, what's the role of an error sanctioning function? We suppose that initially we have these different weights here, different weights. Notice how we've just increased the number of hidden layers here. So now we have 2 hidden layers. So as we've said, we have weights, weights, and weights, which have been initialized to some certain values. And then our aim is to modify this weight such that our model becomes intelligent. And so each time our model outputs a wrong answer, so that is supposing we have this, and then our model outputs something like 0.5 and say 0.6, then our model gets penalized for this kind of outputs because it isn't close enough to this 1, 0. And if we have this kind of input and our model outputs say 0.1 and then 0.9, our model gets penalized because it isn't exactly the correct answer, but it is less penalized as compared to this kind of output here, because here this output is closer to the correct answer. And so over time the model weights get adjusted based on this predicted output difference with the actual output. Now is this difference we call the loss. So our aim clearly here will be to minimize the loss, because if let's consider a simple loss function where we just taking this and subtracting with this. So we have 0.1 minus 0 would have 0, and let's add this other one here. So 0 plus 0.1, it's actually 0.1 plus this 0.9 minus 1, let's say the absolute value, so we have 0.1 again, and that's it. So here we have 0.2, so we have a loss of 0.2. but with this we have 0.5 minus 1, which is 0.5, and then here we have 0.6 minus 0, which is 0.6, and we have a loss of 1.1. so here we have a loss of 1.1 and a loss of 0.2. And so clearly the model performed better with this input as compared to this other input. And so the model or the neural network is going to adjust its weights to ensure that the loss keeps decreasing. And if we could get to this point where our loss, let's plot this out. So let's suppose that initially we have a loss. Let's say we have loss with time. Actually the time here is not the usual time, but we'll call this number of epochs. So from here we're gonna have let's say initially at the first epoch, for example, let's say we had the first epoch, then we may have this high loss, but as we keep on modifying this weights, we find that the loss normally should be dropping. Now we may not get to that point where we have a loss of 0, but at least we're gonna get to some point where increasing or further increasing the training process or increasing the number of epochs wouldn't change the loss value very much. And so at this point, for example, we may stop training, and then once we stop training we get the new weight values, which now have been tuned based on the inputs or the hundreds of thousands of inputs output pairs which we fed into this neural network right here. One other very interesting point about neural networks is that we do not have to be experts in the computer vision domain or a particular domain we are working on in order to come up with very great results. And so unlike before where we needed to get into the details of this type of feature extraction, now this feature extraction is done by the neural network. Nonetheless, this shouldn't stop you from diving deep into computer vision or whatever particular problem you're trying to solve, as this will permit you get even better results compared to another practitioner who doesn't really master the particular domain where you're trying to apply neural networks to solve a particular problem. It should be noted that these weights have been tuned using a gradient descent algorithm. That is, each and every time we want to update this weights, we take the previous weight we have, that's the current state of the weight, minus a learning rate. Let's call this learning rate alpha, or let's just say LR, minus a learning rate times the change in the loss with respect to that given weight. And so after computing W minus the learning rate times this change, we now obtain our new value for W. Let's call this W new or W optimized. This learning rate right here tells us how fast we can optimize the weights. And so if you want to optimize this weights even faster, you have to increase the learning rate. And if you want to optimize the weights in a slow manner, you have to use lower learning rates. Anyway, you should also note that picking too high a value for learning rate will lead to a very lumpy progression in the loss values, while using a very small value or a too small value for the learning rate will lead to a training process which progresses very slowly. And so much care has to be taken while choosing the value for the learning rate. If you want to dive deeper to understanding how neural networks work, you could take up our free building neural networks from scratch course or our deep learning with TensorFlow 2 course. It turns out that the kind of neural network we are going to use in practice when dealing with image data isn't this kind of fully connected neural network where we have the outputs of a given layer, like this hidden layer here, gotten from multiplying the weights, we have seen this already, by the inputs and then adding them up all. So with this new type of neural network, which happens to be the convolutional neural network, we are dealing with a mixture of this type of fully connected layers. Let's take this off. This type of fully connected layers right here, and also convolutional layers. And with the convolutional layers, instead of doing the multiplication of the different weights by the inputs to obtain a single output right here, what we have here is a filter. As you could see here, you have this kind of patch right here which is being passed on the input. So this is your input here. Notice you have this car, which is like the input, and then we have this filter which is passed on this input to obtain this new output. So you notice here that the output looks quite different from the kind of output we have with a fully connected layer. And then from here we have other kinds of layers like the pooling layer. We are not going to get into this in detail into this. You could check out our course on YouTube or on our platform to have all this kind of details. But then again, you have a convolutional layer. See, from here you have convolution again, and this is gotten, or the output is gotten from applying a filter on the previous output. Now when we talk about applying a filter on some input to obtain an output, here's exactly what goes on. So here we have this filter, like in this case, where we're gonna pick here left subel. Let's pick out this left subel. You'll notice already that this output, or rather this input, when passed, or when we pass this filter into this input, we obtain this output right here. Now notice here we have this filter, which is a 3x3 matrix. We have 1 2 3 1 2 3, and then each time we slide on this input image, notice how, see how we slide in, like we start here. Each time we have this here, you should look at this part here on the right side. Let's take this here, take this off. So what we're saying is each time we slide the filter here, you should notice how the output is being generated. Okay, so we have that. You see, each time we have this here, we have an output which is generated. You see, we slide, we have new output, and so on and so forth. So with the role of this left subel filter is to highlight edges. You'll notice that where we have edges, like around these corners, you see around these corners, we have these outputs which are white, like here. You see we have these corners here. See, it highlights these corners. That's the role of the filter. Basically highlights this corner. You can call it a filter or a kernel. So it highlights these corners. And it should be noted that we could have different other filters. So let's pick out a filter like this blur. See the blur in filter. You notice how this initial image here has been blurred out thanks to this filter, and these filters have different values. You notice here how this value changes. Let's change this again. Let's go back to left subel. You see the values here change. If you pick out, let's say, outline, you see the values to change. And these, as we said, are the weights when it comes to convolutional neural networks. And obviously, as we've said already, the role of the training process is to get the best values for those weights, or to obtain the weights such that the whole or full neural network becomes intelligent. Let's take this example we had already. This one, we had this example here. You see that when we apply, let's say we apply left subel again, you see the output we get. We could apply this, you see the kind of output we get. And so clearly from here we see that the values that these kernels or these filters take actually matter, as based on these values we're going to have different kind of output. And so now we understand, at least at a high level, how we obtain this output here, for example, from this input with this filter. It should be noted that the way a convolutional neural network is constructed is such that we have this initial layers made of mostly the convolutional layers, which has that role of feature extraction. So here we're trying to extract useful features, and then we have this fully connected layers which have the role of classification. So like in this case where we want to say whether this is a car, a truck, a van, or say a bicycle, this first layers, this initial layers, permit us extract that information, and then this final layers permit us say which of them, that's based on this extracted information, we are able to say now whether the input is a car or whatever other object. To better understand how convolutional neural networks work, let's take this example of this sample 3D visualization tool by Adam Harley. What this ConvNet right here does is it takes in an input letter. So we could have a number between 0 and 9 passing this input. Let's do that here. Let's say 8, for example. We put in this 8, and then it's able to tell us that what we've put in is actually equal 8. So it's some sort of optical character recognition model. So here you see we have the output 8 from this input that we had written with the hand. Right here you could see the convolutional, this one's here, convolutional and pooling layers, and then here we have the fully connected layers. And as we've seen already, between this convolutional layers, that's between this input for example and this output, let's have this here, between this input and this different outputs, we have some filters, and the role of this filter is to permit us extract useful features from this inputs. Now it should be noted that the input we have here is black and white, so we do not have a 3D input. So from here we're able to get these kinds of outputs. You'll notice that for each output we have a different filter value, and because we have a different filter value, we have in this outputs which extract specific types of information from the input. And if we zoom in a little and try to compare these two outputs, you'll notice that the filter which produces this output is kind of like some horizontal edge filter, whereas the filter which produces this one is a vertical edge filter. So you see that at the edges we have this patches here, but the patches this ones tend to be horizontal patches. You see you have some horizontal patches, whereas here the patches are vertical patches. And so once we get these outputs, we now move to the next layer. Now you'll notice that in this next layer, let's take this off, in this next layer right here, what you would have is max pooling. So what you have here is the same as this, but the only difference is this one is a subsampled or a downsampled version of this one. So that's the role of the pooling layer. And then from here we have another convolutional layer which produces these kinds of outputs, and so on and so forth right up to the end. And then once we get here, now we now get to the fully connected layers. It should be noted that we call these layers right here fully connected, since here each and every value is linked to all the previous values in the previous layer. Whereas here on this convolutional layer, for example, let's have it like this, we get this value by passing the filter through a particular patch on this input. And since we're dealing with a machine learning algorithm, these values are going to be gotten as we train the model with our data. So this means that the values our filters get aren't some predefined values, but instead values they take up as we train the model on our data. And so that's it. That's how this convolutional neural networks work. As usual, if you want to get in depth, you could check out our course. Now you'll see here the output we get. See clearly it shows an 8. So you could always feel free to play around with this and see the kind of output we get.